wanna know the distance to the moon in the sky. Don't need a rocket ship, just need a coin in your eye.
One of the most common questions that I get from students is, how do we know these basic facts about our solar system? How do we know how big the Earth is? How big the sun is? How do we know the distance to the moon? How do we know how far away the sun is from the Earth? How do we know the speed of the Earth as it orbits the sun? How do we know the speed of the moon as it orbits the Earth? How do we know how much mass the Earth has, right? This is 1 kilogram of mass. That's about 2.2 pounds of force on planet Earth. So how many of these makes up planet Earth? How do we actually know that? How much mass does the sun have? And how do we know that number too? So you can go on Google and research all of these numbers and you'll find something, but it almost seems like we're just pulling numbers out of a magic hat. The average person has no idea where any of these numbers came from. And so it's easy to mistrust that information if we don't understand how people found it. But it turns out that people were able to find many of these values even thousands of years ago. So there's some very simple experiments that we can do to figure this information out. And so today I'm going to teach you some of the basic experiments that you could even replicate at home, which can help you find this information without having to trust a scientist. Although we should trust scientists, it's also good to know where that information came from. To figure out the distance between the Earth and our moon is actually a pretty simple exercise. So all you have to do is pick up a coin and hold that coin out in front of your face during a full moon, okay? So the idea is you're placing the coin directly in the path of your eye and you're trying to completely block out the moon, which means you have to find the perfect distance away from your eye to hold that coin. Once you find that perfect distance where the coin just blocks out all of the moon's light, you are ready to do your calculation. So there's 4 things that I've labeled here that you're going to need to know about. The first is capital D coin. So that's the distance from your eye to the coin. So the capital D represents distance. The lowercase d coin, that D represents diameter. So that's the diameter of the coin, which is pretty easy to find. You can just measure that. So you need to know the diameter of the coin and the distance from your eye to where you're holding that coin, okay? Easily measured, both of these things. Then we have the distance to the moon. So that's going to be capital D moon. So D moon is the distance from your eye to the moon. And that's what we're here to try to figure out. And then we have the diameter of the moon, which we're representing with a lowercase d. This is a value that was actually figured out in a prior experiment. In fact, it was figured out as far back as ancient Greece. So we knew the diameter of the moon at this time, and that's going to enable us to figure out how far away the moon actually is. You can actually set up a ratio of similar triangles. And so we have basically the diameter of the coin over the distance to that coin. That ratio, due to similar triangles, should equal the diameter of the moon divided by the distance to the moon. So we set up this equation here. Now here's where it gets interesting. When you do this experiment at home, if you block out the moon with a coin, every time you do it, it turns out that the ratio of the diameter of that coin that you measure divided by the distance of that coin from your face always turns out to be 1 over 110.62. So that means whatever diameter the coin has, it's 110 times further from your face than that number. So that ratio of the coin's diameter to its distance from your eye, due to similar triangles, must also equal the ratio of the moon's diameter to its distance from your eye. So it's just basic math here. And so we can basically substitute this ratio for the diameter of the coin over the distance of the coin and set that equal to the diameter of the moon to the distance to the moon, okay? Now remember, we said that we already know the diameter of the moon from a prior physics experiment, which I might do another video on, but just take my word for it for now. So the diameter of the moon is 3,474,800 meters. So what I'm going to do is replace that here. So let's write the diameter of the moon, 3,474,800 meters. And so now just through some simple math, we can multiply these cross products, divide by 1, and that will give us the actual distance to the moon. And if you solve that, the distance to the moon ends up being about 384 million meters. So D moon is about 384 million meters. So that is the distance from the moon to the Earth. And that is approximately 240,000 miles away, okay? So now we've done it. We've figured out how far the moon is, and we can verify this number today using more advanced technologies, and it turns out to be very, very accurate. Once we figured out the distance to the moon, it actually made it possible to find the distance to the sun from planet Earth. And so what we have to do to figure this out is you look at a moment in the sky when the moon is half full, and you really want to wait till it is exactly half full. So you're looking for half of the moon's face to be completely black and the other half to be exposed to sunlight. So a perfect half moon. And we know if the moon is half full, that means only half of its face is being hit with direct sunlight, which means the sun should be shining perfectly at the moon, and the angle between the Earth, the moon, and the sun at that instant would be 90 degrees. So we're waiting for the moment that the moon is at a 90-degree angle between the Earth and the sun. If you wait for that moment and then look up at the moon and measure the angle to where you see the sun in the sky, that angle, if measured very, very carefully, which it has been done, ends up being exactly 89.853 degrees. And it's really hard to get this much precision, but if you are very careful, you can achieve this. So this is also almost a 90-degree angle. And this isn't really accurate in terms of the scale because, again, the sun is very, very far away. So this should look more like a 90-degree angle, and it does. It almost looks like a perfect 90-degree angle there, but it's not quite 90 degrees because it can't be. There has to be an angle out here, right? And that angle is less than a degree. It's very, very tiny, okay? So anyway, once we measure that angle, and since we already know the distance to the moon, which is side A on our triangle, remember this is a right triangle, so it has sides A, B, and C. C is the hypotenuse, but we need to know this side to figure this problem out. So now we can set up a trigonometric ratio. We're gonna use trigonometry, and we're gonna say the cosine of this angle, so the cosine of 89.853 degrees has to be equal to the adjacent side divided by the hypotenuse. So it has to be equal to A over C, right? Well, A is the distance to the moon, and we already figured that out. So A is 384 million. I wrote the exact number here, so I'll use that. So 384, 382, 376. So over 384 million meters to the moon, as we found in the last example. And that is divided by C, which is the distance to the sun. So now to solve for this, we can just rearrange the sides, and C would equal this number divided by the cosine of 89.853. That's really easy to do in your calculator. If you do that calculation and solve for C, you get 149 billion meters away. So the sun is 149 billion meters away from planet Earth, which is approximately 93 million miles. That is a very far distance. It's much further than most people can comprehend. But on a universal scale, it's really not that far because remember, despite the fact that the sun is 93 million miles away, it only takes light 8 minutes to get from the surface of the sun to planet Earth because light travels very, very fast. Now that we figured out how far away the sun is from planet Earth, we can actually figure out the size of the sun, or what is the sun's diameter across from end to end. And so this is actually similar to how we figured out the diameter of the moon. Basically, you take a sheet, and usually I would recommend a sheet of aluminum foil. It works a little bit better, but you poke a tiny pinhole in it and then hold that sheet up to the sun, and the sunlight is going to pass through that pinhole and it's going to project an image of the sun somewhere on the ground. So usually putting out a sheet of white paper so it's clear, holding up your pinhole, having the light go through it, and you'll see that image projected. So I drew a little diagram here. This is where the pinhole is. So that's the location of that sheet in front of your face. The sun is somewhere far away. This is obviously not to scale. Its light is going to pass through that pinhole and then project an image of the sun on the other side, right? So a very simple experiment you can do at home. And then I labeled 4 things, right? We have the diameter of the sun, which is a lowercase d, the distance from that pinhole out to where the sun is, which is a capital D. And that's what we figured out in our last experiment. Then we have the diameter of the image, which is very easy to measure. It's just what's projected on your sheet of paper. And then we have the distance from that pinhole to where the image is, which I showed with a capital D. And so it turns out we can set up a ratio where the diameter of the image of the sun that's projected on a sheet of paper divided by the distance from that pinhole to that sheet of paper is equal to the same ratio of the diameter of the sun to the distance from the sun to that pinhole, which is essentially the distance of the sun to planet Earth. It turns out if you do this experiment at home, the ratio of the size of the image of the sun that's formed over the distance from your pinhole to where that image is formed, that ratio is 1 over 107.5. So that means the distance from that sheet of paper to where your image is 107 times further than the diameter of the image of the sun that is formed, right? And so that ratio, because it's similar triangles, still needs to equal the ratio of the diameter of the sun to its distance away. And so we also know the distance that the sun is away from planet Earth because that's what we found out in the last experiment. And remember, that distance is approximately 149 billion meters away. So I'm going to replace that with the number 149 billion. And now we have enough information to actually solve for the diameter of the sun to figure out how big it is. And if we do the math, what we get is approximately 1.39 billion meters across. 1.39 billion meters. This is the diameter of our sun. And this is massive. What this number means is you could actually take 110 Earths and line them up side by side, and that would equal the diameter of our sun approximately. So our sun has a diameter that is approximately 110 times the diameter of the Earth. Very, very large. How do we know how much mass the Earth has? That seems like such an impossible question to answer. Finding the mass of nearby objects, that seems easy, but what about the mass of all the stuff that I'm standing on? This is a journey that started all the way back in the year 1687 when Isaac Newton published his universal law of gravitation. And so he said that the force of gravity between any two objects, between you and the Earth, between you and this object, it doesn't really matter. You can calculate the force of gravity between any objects using this equation. And so that's G times M1 times M2 over D squared. M1 and M2 represent the masses of your two objects. So if it's me and this object, this could be M1 and I could be M2. D represents the distance between the objects, and that's easy to measure. And G is called the universal gravitational constant. So this G value actually was not figured out by Isaac Newton. After he died, it was discovered through experimentation by another person whose name was Henry Cavendish. In the year 1798, Cavendish discovered that this universal gravitational constant is equal to 6.67 times 10 to the negative 11th power. And this is written in scientific notation. If you wanted to convert that to standard form, it means take this decimal and move it 11 places to the left. So really what this G value is 0.000000000. So that's 369, a tenth zero, and then a 667. So this is a very, very tiny number. And so if you take that number and multiply by the mass of your two objects and divide by the distance squared, you can calculate the force of gravity between any two objects. So that was the first step. The next step came from simple experimentation, and just by dropping objects and watching them accelerate, we were able to figure out the acceleration due to Earth's gravity, and we know that that is equal to 9.8 meters per second squared. We also know that if you wanted to calculate the force of gravity that's pulling any mass down towards the Earth, it's just mg, where m is the mass of that object, and whoop, and g is the acceleration due to Earth's gravity, or 9.8. And so if this equation calculates the force of gravity between any objects in the universe, and this equation calculates the force of gravity pulling stuff down on Earth, since we're talking about Earth's gravity, we can just set these two equations equal to each other. So we're going to say that g m1 m2 over d squared, this force of gravity equation is equal to this one. So that's equal to mg. Now I'm going to make a slight modification here. Instead of m1 and m2, I'm going to replace these numbers or these variables with a little m and a big M. The little m is going to represent the mass of any object that's on Earth, And the big M is going to represent the mass of the Earth itself. And that's what we're going to try to calculate here. So if you look at this equation, there is a lowercase m on both sides. So that's going to cancel out. And so on the left, we are now left with g times m over d squared. And on the right, we just have little g. And so we know lowercase g. Remember, things fall at a rate of 9.8 meters per second squared. So that's going to go here. That's the 9.8. We know g, the universal gravitational constant, so that can be substituted here. And we know the distance between objects on Earth to the center of the Earth, because at this point in time, we had already figured out the size of the Earth. So this d here is actually just the distance between things on the Earth's surface and the center of the Earth. And if you think about it, that's just the radius of planet Earth, okay? So now I'm going to do some rearranging. And so I'm going to rewrite this equation in terms of m, because remember, we're trying to figure out the mass of the Earth. So that's going to be g times d squared over capital G. And because we know all of these things, we can just plug them in and actually solve for the mass of the Earth. So we'll start with lowercase g. Remember, that is 9.8 meters per second squared. That's the acceleration of things that are falling on Earth's surface. D is the radius of the Earth in this example, which is 6,370,000. I have the number here, and that's 972. Oops, 972. And that's in meters. So that's the distance between the surface of the Earth and the center of the Earth. And of course, that distance has to be squared according to this equation. So that's going to be squared and then divided by the universal gravitational constant, which is 6.67 times 10 to the minus 11 power. And so if you do this math, so 9.8 times this huge number squared divided by this number, you get the true mass of the Earth, which ends up being 5.97 times 10 to the 24th kilograms. So how big is this number? Well, 10 to the 24th power means that this decimal place can be moved 24 places to the right. And that means there's a lot of zeros here. In fact, this number is so big, this is equal to 5.97 septillion kilograms. Or you could say 5.97 trillion trillions of kilograms. So remember that 1 kilogram mass that I had? Imagine 5.97 trillion of those, and then imagine another trillion sets of that. And that is the amount of mass that our planet has. Insanely big, but it's nothing compared to the mass of the sun. Since we know how far away the sun is from the Earth, as we saw in our previous experiment, we can now calculate the velocity of the Earth as it travels around the sun. And it's actually quite simple to do this. And so the first thing you have to do is observe how many days does it take the Earth to go around the sun. And everybody knows this number. It's about 365 days. It's actually 365.25 days. So there's an extra quarter of a day. And that's actually why we have a leap year every 4 years, to account for this quarter day. But anyway, this is the amount of time it takes for the Earth to orbit the sun once. And so we're trying to figure out its velocity. How fast is it going? And in physics, to calculate velocity, it's simply distance divided by time. And so how much distance does the Earth travel to get around the sun once? Well, if we assume that it's a relatively circular orbit, which it isn't really, it's actually an elliptical orbit, but for this calculation, you can get an average velocity by assuming a circle. Well, what is the distance you have to travel to go around a circle? Well, that distance is the circumference of the circle. And the circumference of any circle is just 2 pi r, right? And so r, in this case, is the distance from the Earth to the sun, which is known. And that's divided by time. Speed equals distance over time. Well, the time is also known, 365.25 days. So if we plug in all of this information, we have, remember, the radius in this circle, which is the distance from the Earth to the sun, is 149 billion meters away. So I'll plug in 149 billion, that's 9 zeros, and then divided by 365.25 days. But remember, this is, for velocity, we're trying to calculate meters per second. So that means this time needs to be in terms of seconds. How many seconds are in a day? Well, we know there's 24 hours in a day, right? 24 hours in one day. And there's actually 3,600 seconds per hour. And so that means this bottom term has to be multiplied by 24 and by 3,600. And if you do all this math, what you calculate is the actual velocity of the Earth on average as it goes around the sun is approximately 29,785. 29,785 meters per second. That's almost 30,000 meters per second. We're traveling very, very fast. But what is this number in miles per hour? This is over 66,000 miles per hour. That is an incredible velocity as we travel around the sun. Remember, this is an average because our orbit is not a perfect circle. So when we're close to the sun, we're going to be going actually a little faster than that. And when we're further out, we're going to be going a little bit slower. To figure out how fast the moon is traveling around the Earth, we use the exact same procedure. So instead of showing the Earth going around the sun, I have a diagram of the moon as it travels around the Earth. It does have a fairly circular orbit. And again, it's not really a perfect circle, but we can assume a circle to calculate the average velocity of the moon. Just be aware it's going to be traveling a little bit faster sometimes and a little bit slower other times. And so the time is what we need first, right? How many days does it take the moon to go around the Earth? It only takes 27.32 days for the moon to go around the Earth once. So this time is 27.32 days, okay? And so remember, to calculate a velocity, it's just distance divided by time. And the distance that this moon has to travel to go around the circle once is the circumference of the circle, which is 2 pi times r. And r is the distance between the Earth and the moon, which we already discovered in a prior experiment, right? So we have 2 pi times 384 million meters, because that's the distance from the Earth to the moon, divided by the time that it takes the moon to go around the Earth, which is 27.32 days. But remember, our velocity is going to come out in meters per second. So that means the unit of time can't be days. It needs to be in seconds. So there's 24 hours per day, and there's 3,600 seconds per hour. And so if we multiply this bottom number by 24 and by 3,600 and do all the math, we get a velocity of the moon on average 1,023 meters per second. So the moon is traveling just a little bit more than 1,000 meters per second, or about 2,288 miles per hour. So this is 2,288 miles per hour. Now compare that to the velocity of the Earth as it travels around the sun. Remember, the Earth was going almost 30,000 meters per second. The moon is going about 1,000 meters per second. So it's only about 1/30th of the velocity of the Earth, much slower. How much mass does the sun have? How can we possibly figure that out? Well, the first thing we have to do is draw a little diagram to understand what's going on here. So here's Earth, and Earth is orbiting around the sun in a relatively circular orbit. It's not really a circle, but we're going to approximate it as one. And so it's going around the sun. And so there's some kind of force that's pulling the Earth in towards the sun, because if there wasn't a force, the Earth is an object in motion. It would just continue in motion and go into space. And so as it goes around the sun, anytime there's a force pulling something in towards the center of a circular path, we call that a centripetal force, or FC. So that's the force of gravity pulling the Earth towards the sun and preventing it from leaving, right? But we already did figure out the velocity of Earth. We know how fast the Earth is traveling around the sun, so we're going to need that later. And we know the distance from the Earth to the sun, which I've labeled as r. And the reason I label it r is because, remember, this is a circle, and so the radius of the circle is the distance from the Earth to the sun, okay? So what is this centripetal force equal to? Well, any centripetal force is equal to mv squared over r. That's how you calculate it. M is the mass of the object in orbit, so that will be Earth's mass, which is known. V is the velocity of that object. Again, we know the velocity of the Earth, and that's going to be squared. And R is the distance between the Earth and the sun, which is also known, okay? So that's the first equation. Now remember, we said this centripetal force that's pulling everything in towards the sun is the force of gravity. So we can say that the force of gravity is equal to Gmm over d squared. And remember, this is called the universal gravitational equation. So you take this constant, capital G, which we know, times the mass of one object, in this case the Earth, times the mass of the other object, in this case the sun, and multiply by the distance between them squared. That calculates the force of gravity. Now I'm going to replace this d with an r, because that distance is what we labeled as r in our diagram. And so what do we notice? We have one equation that's the centripetal force, another equation that's the force of gravity, But those two forces are the same thing. They're one and the same, which means I can set them equal to each other. So mv squared over r, this top equation, should equal gmm over r squared, the bottom equation. And so what else do we notice now? Well, both sides of this equation have a lowercase m and an r. So if I multiply this side by r over m, these r's will cancel and these m's will cancel. So I got rid of two things. But if I multiply the left side by r over m, I also have to multiply the right side by r over m. And so this r will cancel with this r, and that means this r squared becomes just a regular r. And then this m up here cancels with this m. So at the end of the day, what we end up with is v squared is the only thing left on the left side, and on the right we have gm over r. So v squared is equal to gm over r. But I wanted to solve for m. Remember, we're interested in the mass of the sun here. So I'm going to rewrite this equation. So it's m equals v squared times r over g. And so with this simple equation, the mass of the sun is just equal to the velocity of the Earth as it goes around the sun squared times the distance between the Earth and the sun, which we called r, divided by g, which is the universal gravitational constant. And just by plugging in those three knowns, we can actually figure out the mass of the sun. The velocity of the Earth as it orbits the sun is a little under 30,000 meters per second. So it's about 29,785 meters per second, very fast. The r in our diagram, the distance between the center of the sun and the center of the Earth, is about 149 billion meters. So very, very far away. Remember, that's approximately 93 million miles away. And g, the universal gravitational constant, that's always constant. It is 6.67 times 10 to the minus 11th power, which is a very tiny number. So if we plug all three of those items in, we get 29,785 squared, because the v is squared, multiplied by the distance between the Earth and the sun. So this will be 149 billion. So that's 9 zeros meters. And then that's divided by g, 6.67 times 10 to the minus 11. And so when you plug all of that in and calculate the mass of the sun, you get 1.99 times 10 to the 30th power kilograms. This is the mass of the sun. So remember, 10 to the 30th power is an insanely large number. It means this decimal here, you have to move it 30 places to the right. So how big is this really? How many kilograms of mass is this? This is equal to 1.99 million trillion kilograms. It's so big, it's hard to even fathom that amount of mass. So remember, Earth's mass was a 10 to the 24th power term. And so the mass of the sun is actually about 330,000 times more than the mass of the Earth. So that's very huge. That's a massive difference. Imagine 330,000 Earth masses is approximately equivalent to just one mass of the sun. And that's why everything in the solar system orbits the sun, because the sun's mass is just enormous, enough to warp space-time around itself and keep everything in orbit. And there you have it, a handful of very, very simple experiments that have been done throughout the ages to figure out the size of objects, the mass of objects, their distances apart, and their speeds as they move through our solar system. All these numbers that you hear and take for granted, just know that they are carefully discovered through experimentation and through calculation. So nothing is made up. Scientists are not trying to lie to you. It's all a product of hard work over many, many hundreds, if not thousands of years of research, experimentation, and analysis.
You wanna know